KKT condition, dual problem, Lagrange multiplier. These are keywords to understand the next step. And essentially, these three steps are not undergrad level, so it's very advanced topic. So I want to skip the details of the next step, but if you really want to fully understand every single step of support vector machine, you have to read some materials on KKT condition, dual problem, and Lagrange multiplier. Here I just want to explain the result of Lagrange multiplier and why this is good to understand maximum margin classifier, support vector classifier, and support vector machine. Okay, so previously the optimization problem was minimization problem with parameter beta and two-norm square with constraint sum of I want to n max 0 1 minus yi f beta xi. This was epsilon I star less than or equal to c. This is convex function with respect to beta. So this is convex optimization problem. And this also convex set with respect to beta. Okay. In this case, this is constraint. So if you have this constraint, some convex function less than or equal to 0 constraint, you can multiply some constant called Lagrange multiplier and bring this term to the objective function line. So essentially you can make this minimization problem with respect to beta vector norm square plus Lagrange multiplier times I want n max 0 1 minus yi f beta xi minus c. Okay, because when you move c to here, this is some function less than or equal to 0. Okay, and here there's no constraint, convex objective function, so you can find beta star that minimize this objective function. Let's say this is some function lambda, which is the result of this function. The dual problem is maximization problem with respect to the Lagrange multiplier lambda, and this the result of the optimization problem. Since when you control the Lagrange multiplier lambda, you will have different optimization solution. This is function of lambda. Okay, the solution of this problem is function of lambda. Okay, so dual problem solve another optimization problem with respect to the Lagrange multiplier. But here the Lagrange multiplier has constraint lambda is must be greater than or equal to 0. Anyway, with this C and lambda, and when you solve the dual problem, essentially lambda converts to some point where your solution beta satisfy this equal to 0. This comes from KKT condition. If this not satisfy, lambda must be 0. Okay, and you don't need to worry about the separation condition. When all the data point is very well separated, then this inner term always equal to 0. In the case with some sufficiently large C, you don't need to worry about the constraint. In the case, the lambda will be equal to 0, and you just need to minimize the beta. But when you decrease the beta go to 0, this term essentially cannot be 0 for any point xi. So essentially, I believe this constraint always acts some role. So in the end, this constraint equal to 0 by KKT rule, and lambda is non-zero, and there is some lambda value that make your beta satisfy this equal to 0. And that is the solution, essentially. This is the KKT optimization condition. Okay? So yeah, maybe this is too complicated or too difficult to understand at this moment. That is very natural thing. This is not undergrad level optimization knowledge. This is totally graduate level. Well, it's good to know, right? Okay. So anyway, we have to solve this problem, and there is some constant lambda c, Lagrange constant lambda c, that make this equal to 0. Okay. And when you focus on this optimization problem, essentially the most important part is this: beta norm square plus lambda c times n max 0 or minus yi fb xi. Because c is just constant for this optimization problem with respect to beta, this term is nothing. We don't need to care about the c, and we just need to find beta that minimize this function. Okay, so how to solve this, and what will be the solution? Okay, naturally, when you have some convex function, the optimization problem very easily be solved. You just need to find the zero gradient point. And what is the zero gradient point? So when you take the gradient, then this is 2 beta 1 to beta p comes from beta norm square, and from the remaining part, max. And this is equal to inner product beta n xi minus lambda I12 n alpha I y I xi12 xip equal to 0. We have to find some alpha I that make this equal to 0. And here alpha I must be 0 when this term is activated. When yi f beta xi strictly greater than 1, then this term is just constant. So when you take the gradient, this is 0. So alpha I equal to 0 when this value is strictly greater than 1. Alpha I is equal to 1 when yi f beta xi is strictly less than 1. Alpha I can be anything in between 0 and 1 when yi f beta xi is equal to 1. Why? When you look at this hinge loss function, it looks like this. It's non-differentiable at this point. So this is again some advanced topic, sorry. When you have a non-differentiable point, then alternative way is take subgradient. Subgradient is all the line that do not cross with your function value. Okay, so all the line in between here in this case -1 and 0, you don't have any cross. Okay, so that's why this alpha I value can be in between 0 and 1. Right, so the bottom line is your beta vector solution just depend on your input xi and output yi such that yifbxi strictly less than 1 or fifbxi is equal to 1. What is the physical meaning of these two conditions? What is the physical meaning? Essentially, when you have two class and when you have decision boundary comes from your maximum margin classifier or soft vector classifier, and there is margin point, margin distribution. fibxi equal to 1 means the xi data point located on the margin boundary. Your data point on the margin boundary. It means fi f beta xi equal to 1. What is the meaning of fyi times f beta xi strictly less than 1? From this condition, the meaning of this is your point is not this side, but disobey your marginal condition. Your y value disobey your marginal condition. All these points satisfy this condition yi f beta xi less than 1. And this point essentially decide beta value. The solution beta value just depend on this data point. If your data point well separated and belong to this marginal area, we don't care about the point when you draw the decision line. So all the data points satisfy this condition are called support vector, because this support vector decide beta boundary. Okay, they decide the beta value, so they called support vector.